And our next speaker will be Andrea Coronetti. And Andrea, I would like to invite you to share your screen. And Andrea has received his PhD in the applied physics from the University of Jyväskylä in Finland, and on the topic of relevance and guidelines for radiation effects testing beyond the standards for electronic devices and system use in space and accelerators. During and after his PhD, he has worked for 6 years in the European Organization for Nuclear Research, or mostly known as CERN, and has been involved in the implementation of several European Union-funded projects, such as the Network of European Facilities, RUTNIX, which we're gonna see a presentation a bit later, and the High Energy Ions for Electronics Testing HARTS. Currently, Andrea is working as a radiation and components engineer at the NICS cargo capsule for the ISS and the commercial space station at the Exploration Company in Germany. And Andrea will give us now a presentation about radiation effects in electronics. And with that, I would like to give the stage to you, Andrea.
Thanks a lot, Jan, for the nice introduction. So I'm going to talk about radiation effects in electronics. I think that before we delve directly into that, I make a small bridge between what was presented before and this talk, because we need to keep in mind which are the most important space radiation particles for us. Of course, there are ones of solar origin, which then, let's say, for low Earth orbit satellites are then divided in two sources, which are the trapped radiation belt, mainly made with protons and electrons that will contribute to radiation effects in electronics, as well as the solar particle events, which again include proton, electrons, and some ions, which are stochastic and both in time and magnitude. And then there is a third source, which is galactic cosmic rays that you mentioned before, Jan, which is mainly protons and ions, which is very relevant also for electronics devices. So now that we know a bit what are our space particles, we see an ion, and that it's ready to interact with a small schematic of a transistor, from a MOSFET transistor. So you see the gate oxide on top, the silicon body underneath, the well, and a metal contact that it's used normally to collect electron rolls through the channels. So let's see what the particle does when interacts first with the oxide. It generates electron pairs by interacting with the electron cloud of the various atoms in the silicon oxide. And due to the fact most of these electron pairs may recombine immediately, but due to the fact there is an electric field around, they can be spread over and get trapped into the oxide traps, and generating what we call then total ionizing dose effect, which is something that it's basically affecting the capability of the device to switching. This is mainly due to the fact that even if there is an electric field usually across the gate oxide, the let's say electron pairs tends to separate from one another and create a secondary electric field that can change again the switching capability of the device. Also, charges that get closer to the interface where there is the channel of the transistor can generate interface states that also may reduce the, let's say, the lifetime of the minority carrier there and also affect the switching of the transistor. The journey of the particle goes on and it reaches the silicon. Also here it interacts with electronic clouds of the atom and generates electron pairs, and either electrons or holes may be swept into the metal contacts and generate what we call a single event effect, which typically can be then subdivided in further amount of different events. What we've seen here, it's transient, so it's something that basically happens and for a temporary amount of time and then disappear. But there are also other errors and potentially destructive effects that can happen because of this generation of electron pairs that triggers also some regenerative mechanisms in the silicon that can bring to the destruction of the device. Finally, our particles can also interact with the nucleus of atoms that are present in the lattice of the silicon itself and displace the nucleus from its original position, creating what we call vacancies as interstitials. and the phenomenon that is called displacement damage, which also affect sensibly the way the device will behave, and we will see all these effects soon enough. So this is the first panoramic of the three effects. We've seen that electron pairs can cause total ionizing dose and single element effects, whereas the interaction with the nucleus creates displacement damage. Another more historical way to see these effects is to consider the ones that are stochastic with respect to the ones that are cumulative. So basically, the ones that are stochastic are those that can happen in a random way all along the lifetime, the useful lifetime of the device. So they can happen at the beginning of the lifetime or at the end of it. Whereas total ionizing dose displacement damage basically requires a build-up of defects before we can see an effect, and basically they define, let's say, the wear-out failure of the device itself. So one way also to classify single element effects is also to, in terms of various families, in terms of what is soft, what is hard, and what is destructive for the device itself, is also to see how you can intervene sometimes to either reduce the impact on the device or reduce the failure rate of the device. So normally soft errors are those that you can try to reduce both the impact and the failure rate for the device. So and we call them single element transient, single element upset, and single element functional interrupt. For non-destructive single event like CHAP, basically you can try to reduce the impact, but you will not be able to affect the rate unless you really change with the design of the device. And then there are also destructive events that you basically cannot reduce neither the impact or the failure rate, in the sense that unless you really use the device in a very different way, those will completely destroy the device. You cannot do much about it. To talk about single event effects, we have to also clarify that this is typically caused always by an ion in space, because there are primary ions coming from galactic cosmic ray or solar particle events that do this by direct ionization. So a single particle passes through and there's enough high linear energy transfer, which is basically defining how much charge you are, or how many electron pairs you are able to deposit per distance as a function of the density of the material. And they typically have also very long path in the sensitive area, so they can deposit a very large amount of charge there. Nevertheless, protons can also, in particular those that have high energy, can also cause single event effects. However, not by their own linear energy transfer, because this is very small, but typically after interaction with the nucleus of silicon, that can happen in various through various mechanisms that let's say the fact that this secondary ion is set into motion with it allows it to interact with other electron clouds and generate other electron pairs. So in the end, single event effects can be caused by both primary ions and protons, but the protons are actually in indirect ionization because it's a secondary ion that causes them. Okay, now we see more or less one by one the various single event effects. So we start with the transient, because more or less there is always a transient that triggers some of the others. So basically this is a very fast current or water spike that we can see as an output from a transistor. You see a simulation of what happens when an ion track interacts with the silicon layer. And you see that basically these charges are collected all around the metal content, and then by drift, which is caused by electric field, and diffusion, which is caused by the difference in density between the electrons or holes, depending on the doping. These get collected completely, and basically you get this charge that we see here. That can be a spike both in current or in voltage into your device. It can be analog or digital, so you can, and depending on what captures it, basically afterwards it gets this name. And this is an effect that is very easily triggered. Usually it comes with very low, it doesn't require much charge to trigger, so both low AT ions and energy protons can cause it. The fact of the device is that, well, for analog device, basically you get this transient at the output of the device, but the device by itself does not fail. It will still continue to operate. Instead, if you have a digital component, you will have basically the this transient, if it is happening and during a clock cycle, it can get captured by stable element and resulting in ICU. Effect on system is that, of course, it can alter the functioning of the devices that captures it. So you could have create a single, what we call single element upset. So you'll have data that is corrupted or can be misinterpreted. It can command the switching function, let's say, of another device, or reset the other device that receives this single element transient. For instance, if we have a transient to 0 volt on a microprocessor, it can trigger its reset or get it stuck. The single element upset is happening typically in logic elements, and it's what we call bit flip. So you are storing information in a logical element or in a memory element as either a 0 or 1, logical 0 or 1, and due to radiation, you flip it from 0 to 1 or from 1 to 0. It can be a single one, or a single particle can also cause multiple of them. So you can have an extension of it in the surroundings of it. And it's also an event that is very easily triggered by low-energy ions and high-energy protons. Concerning the device, of course, you have temporary loss of the reliability of the computations that you are doing when you are reading from that logic element of the memory. You will have potential loss of information in the storage device, and of course, if it happens in control logic, it can result in a third type of single element effect, which is the single element functional interrupt that we will see in the next slide. SUs can be also tricky because even if they are soft for the device, they can be potentially destructive for the system or disruptive for the system, because they may trigger an erroneous command if they are not captured, if it's not asserted that there is a problem. Of course, you will have data corruption and integrity loss in what you store in your let's say memory storage elements. Or you may define also another device in an unknown state that doesn't know exactly how to behave, or cause the reset of the other device. So I didn't have a better picture than the blue screen of that to describe a safety, because this is what it is. It's just that basically, as a consequence of SU in control logic, your device becomes temporarily unavailable, it hangs, it tilts, something like this. So depending on its magnitude, it may require even something as critical as power cycle to be clear. And also, having originating by SUs is also an event that can be easily triggered by low-energy ions and high-energy protons. For the device itself, we see that there is a temporary loss of function of the device, or even loss of communication. So in particular, if this happens in very important element of your system, you may have that another device interrogating this device will not get an answer, or will assume that it is getting an incorrect answer or something like this. So you may have a partial or temporary loss of functionality, or let's say a degraded mode of operation. Of course, this information may also be misinterpreted, and of course, you must have something. If, for instance, your onboard computer gets stuck and it's the brain of your satellite, you must have something to recognize the failure, to detect it, to isolate it, and to recover it. Otherwise, you are basically using the system as well. We move a bit into the towards destructive single element effects here. So here, the first one that we see is a single element latch-up, which would be non-destructive or destructive. Here you see a schematics of what happened in the device is that due to the particle strike, basically you activate in CMOS technologies the regenerative circuit that is due to the fact that you have a PN-PN junction there. And then from the first instance, you basically get something you trigger this regenerative circuit, and you get a very high current absorbed by these circuits in this area, which can lead to thermal destruction of the transistor. This is a bit less likely to occur with protons. It's it requires usually an ion that can have a sufficient ILET, but also can go sufficient distance, so that the amount of charge that is deposited is sufficient. In terms of effect on the device, it could be a temporary loss of function. but it also could be, or let's say the effect could be similar to the ones of the SEFI, but they could be also more important because you can even lose completely the, let's say, reliability of function of parts of the silicon, of impact the reliability, long-term reliability of the device, or completely lost the device in case it's you don't have anything to limit the current that is absorbed by the device. In terms of effect on system, again, in theory, it's very similar it looks similar to a SAFE in the sense that you can have temporary loss of functionality if you can recover from it, or you can go towards something which is more permanent and destructive for your integrated circuit. The last two are the ones that typically affect power devices. The first one is a single event burnout. So again, it's coming from the fact that you activate parasitic BJT, let's say, in this case NPN, N-channel MOSFET, that has a regenerative, let's say, behavior, or let's say avalanche breakdown that sets into motion a lot of electrons, and you see basically a current spike from your device in the current between the drain and the source that could be go up from let's say an off condition from several orders of magnitude. It is typically destructive if you don't have anything to limit the current, of course, because this is a very high current that you are generating in a very small space, so you are going to have, again, thermal breakdown. The sensitivity is very strongly dependent on the device bias, so there are ways which we call derating to make a device less sensitive to single event burnout, which means reducing let's say the bias voltage so that it operates in a way that it's less likely to generate this to activate this NPN. And again, it's possible with protons, but it's typically very likely with ions. Here you can see again that the visible damage that you can have when this kind of effect happens. In terms of the effect on the device, it's basically that the device is permanently having a high off current, so it's basically never, let's say, off, but it's always consuming power, and potentially we can say that the device is completely lost. And again, this could be a partial loss of functionality or degraded mode of operation, depending on what this device is responsible for the system. Because in theory, if the let's say power MOSFET is always on, you are already driving a current that it's already very high, so you will not see effect. But if you try to turn it off or this is switching, of course you will have a current that stays there permanently. So in theory, it could even, if it is in your power system, it could even bring down your entire system. The last one is the single event gate rupture. So this is a bit different, but again, it happens in power MOSFET. It is a generation of a conductive path inside the oxide, gate oxide. So basically, due to the fact that there is after the ion stack, there is this column of charges between the gate oxide and the epi layer. You have a very strong electric field that basically generates breaks the gate oxide and generates a conductive path. So then in the end, basically, drain, source, and gate are all shorted together. So this is always destructive. You cannot prevent it. Again, you can save yourself with the fact that you can apply derating. So reducing bias will reduce the probability that this can impact your device. And again, it's typically very likely to occur with ions and a bit less with protons. Since you lose basically the gate oxide, your separation, basically you lose the capability to turn on and off the device. So basically it brings to essentially complete loss of the device. And again, depending on what is the function of this power MOSFET in your system, you can have different kind of either partial losses or potentially permanent losses of the entire system or a subsystem. I think it's also important to bring you a bit some let's say nomenclature here, because it will be needed for the next presentation. So the SE cross-section. So single event cross-section is a way that we use to define which is the sensitive area of integrated circuit. And then we used to calculate later on the probability that an SE will happen, because this is the effect is stochastic. This is defined as when you do a test, as the number of events that you see divided by the fluence of either ions or protons that you are using in your test. And basically what you get is that you have typically this kind of response curve as the cross-section of the device as a function of linear energy transfer for ions or energy for protons, where you have, let's say, some important values, which are the LT threshold, which is the minimum LT at which you can trigger that kind of single element effect. So the ions has enough, creates enough electron hole charges to actually trigger the event itself, and below it would just bring you to a transient that does not bring to anything else. And then the saturation cross section, which is the, let's say, the maximum size of your sensitivity or inside your devices, which can never be larger than the size of the die of your device. Physically speaking, it can be as large as it is, but not larger. And typically it's smaller because the area of the die that is sensitive is typically smaller. And the fact that you have this, let's say, kind of, not let's say a step function, but you have this what we call typically weighable function, is related to the fact that you are activating more and more of this area as you move high with the LET. Finally, also the concept of safe operating area, which is important for the destructive event, particularly single event burnout and single event gate rupture, which is what we were talking about before. So the rating. So it means that you go and when you test, you collect data with different ions at different biases for the gate and the drain. And you see that your device never experiences SCB and CGR under this curve. With then the curve that you need to use depends on your mission, let's say, because every ion has a different LET, and you will have a certain LET threshold for each of your mission. But I guess this we covered also a bit more in the rational assurance. Speaking a bit later, I'll try to speed up. Total ionizing dose. So we have seen before that this generation of build-up of trapped interface charges in the silicon gate that basically change the switching capability of your MOSFET. So it could be different in NMOS and PMOS, but basically what happens in NMOS because of the oxide traps is that your device IV characteristics move towards the axis, so the device remains on even when you apply a voltage that should turn it off. Whereas the PMOS say threshold voltage moves to a value which is lower and lower, which makes it harder and harder to switch it on. This is measured typically in radiation in RAD, in silicon or silicon oxide, because we have seen that this is mainly an oxide thing. And the particles of interest for this are electrons and protons. There are many things that can happen. Of course, there are the change in the switching characteristics, but also the generation of potentially leakage current in power and then increasing power consumption of your device. You can have loss of information, loss of switching capability. So loss of information, I mean that basically at some point your transistors are so compromised that they cannot hold anymore whatever logic state you have put into them. Or the device, of course, at the end of the day, the device can be considered completely lost when the dose becomes too high. So the effect at system level could be always the same as a destructive SE at the end of the day. Of course, you can have also parametric drifts due to the total ionizing dose, which means that you will be affected by total ionizing dose before the device potentially fails completely. Which means that your device may start misbehaving before that. And also there is a strong dependency on the TAD with respect to particle electric field, whether it's applied or not, the temperature and the dose rate itself. Particularly the dose rate, you can have this enhanced low dose rate sensitivity, which is something that you see when you have real-time dose, as opposed to the accelerated dose rate that you have in a facility. And typically you have a total dose rate effect whenever you basically then apply annealing, and you see that the degradation of the accelerated test is much lower than the one that you get from the low dose rate test, and this affects mostly bipolar devices. Also, annealing is important to be done after TID test, because after you have, let's say, applied dose up to your desired level, you will have a degradation. But after annealing, you can have very different behaviors. The device, typically, you would expect it to recover it, but sometimes it just keeps degrading even more and more, which was what we call negative annealing. Or otherwise, it goes out of spec on the other side, which is what we call rebound annealing. Finally, the displacement damage, you will see a nice animation going on that explains that this is much more complicated phenomena than what you see here with the generation of just interstitial and the vacancy. But basically, when you displace an atom, here you see basically that this particle is displacing a first atom here, which is called the primary knocked atom, and then it's interacting here further with a second atom here. It's something that basically also provide additional damage to your system, and it's mainly caused by electrons and protons in space. And here we see an effect because we see that protons basically provide a much higher damage with respect to cobalt 60, which are only photons that can only produce total ionizing dose and not displacement damage. The effect of the device depends on the nature of the device, of course. There is direct current increase in the imagers, random telegraph signal as well in these kind of devices. And then it affects basically optoelectronics as well. So you may have light emission reduction in diodes, the current transfer ratio that reduces in optocoupler. You can generate stuck bits in memories. That could be permanent or intermittent. So there are bits that basically are not rewritable anymore, whereas for an SU, basically you can correct it. And of course, the mechanism that is responsible for solar cell degradation. Again, it's very similar. You can have temporary or permanent losses of functionality. I think I'm very late, so I will probably skip the radiation effect variability, but which is mostly related to the use of, let's say, non-space grade or not IRL devices, but on using on commercial devices. And the fact that you can have different radiation effect response from devices that because they're maybe manufactured or assembled through different lines. This is a conclusion slide that just summarizes a bit everything that I've said so far, and the key points that maybe to keep in mind for every of the three effects. And I think I'm not going to take more time from the other speakers and just close it here. So back to Jan.
Thank you, Andrea. I know it's really a lot of, let's say, content that needs to be explained just by introducing radiation effects to electronics. So therefore, I really much appreciate your work here and giving us a nice introduction about radiation effects to electronics. Yeah, as you said, we are having a tough schedule, and maybe just one question that we can simply give you to just have one question open. Why do protons are rarely triggering destructive SEEs like SELs or burnouts or gate ruptures? Can you shortly comment on this?
Yes, sure. Well, basically, the proton is a particle that is charged as well as an ion, which is, let's say, an ensemble of protons and neutrons that have a much higher charge. But the proton itself is does not have high capability to create electronal pairs. So the direct ionization from the proton will not cause that, let's say, generate enough electron pairs to let's say, go beyond the LET threshold of the device and trigger itself the destructive event. Whereas an ion, basically, it's much more effective into this because it deposits several orders of magnitude much more charge and generates several orders of magnitude higher amount of electron pairs. The proton generates this by colliding with a nucleus, which means that, but it's the nucleus is much smaller than the electron cloud of the atom. So the probability that this happens, it's much smaller, like hundreds of thousands smaller than interacting with the electron cloud. So also the probability that a proton will generate a secondary ions that has enough, let's say, ionizing capabilities or electron pair generation is much is smaller. So that's the reason why basically at the limit, an ion with a very high LET will always cause an event, whereas a proton, only a proton in several hundreds of thousands will do it.
Thank you, Andrea.
I hope
thank
this
you
is
one more time.
not too physically technical, but
it's hard to explain to non-experts in this way. But yeah, I really much appreciate your presentation once again. And with that, I would like to hand over to our next speakers, which will be